Hello. In the last two lectures, we looked at kinematic as well as elastostatic approximation for the large displacement behavior of a cantilever beam. And at the end of the last lecture, we also talked briefly about pseudo rigid body modeling for beams or slender beams that exist in compliant mechanisms. Let us look at that in detail today with some example that will work out next week lectures. So, this pseudo rigid body modeling, as also known as an acronym PRB, pseudo rigid body modeling, pertains to approximating the behavior of a cantilever beam undergoing large displacements. The first thing is kinematic approximation. There a circular arc is taken as approximation to the locus of the loaded tip of the cantilever beam. That was done by Burns and Crossley, as we have discussed already. And we also have another important approximation, which is elastostatic approximation, that is under the action of static loads, the deflection of the cantilever beam, the resistance that the beam offers can be captured with a torsional spring, as was done by Howell and Meadha in 1995, where they saw that this in the spread, which is very narrow, of this equivalent spring constant, torsion spring constant, that can be approximated with some number. In this particular example, it was 1.98 Newton meter per radian. So, having these approximations for kinematics as well as elastostatic behavior, at the end of the last lecture, we also talked about this pseudo rigid body model. That is, if I have a cantilever beam of length L fixed at one end, free at the other end, meaning that it can have load in any direction. That is, there will be transverse component to that load as well as the axial component, which can be tensile or compressive. Then we can replace that cantilever beam with a rigid crank of length gamma times L, where gamma is called the characteristic length factor for the beam, which is on the average is taken as 0.85. It was 0.8333 based on the kinematic approximation that Burns and Crossley had done. Let us refined by Howell and Meadha to 0.85 on the average, where you maximize the angle, what is shown as psi here, that angle as large as possible, so that this approximation with circular arc holds for the locus of the loaded tip. And this one, if you use, that is PRB, pseudo rigid body model, if you use, you can forget about the cantilever beam, meaning that the effect of the cantilever beam is captured at the free tip. One end is anyway fixed. If the beam is as part of a compliant mechanism, if one end is fixed, other end is free, meaning that there is no movement, then we have this nice pseudo rigid body model, where it can be between two bodies that is connected, those are connected to the beam in question. So, we can replace that beam with a rigid body with a torsion spring, then we can go back to the literature of kinematics and do our analysis and synthesis comfortably, and then come back when you want to have compliant mechanism, replace that rigid body with torsion spring back to an elastic beam, and that is how this is going to work. That is the concept of the PRB. So, let us look at that. That is, this beam over here is replaced by this rigid crank. So, this is the rigid crank, where the force can be any which way. There will be a transverse component as well as an axial component. N is the one that relates both of them. N can vary, as it is shown over here. For various values of n, you have different value of this characteristic factor, the gamma L. That is, you do not take the rigid body as long as the elastic beam, but only take a fraction of it, which is the fraction is controlled by this gamma. For various values of n, that is depend on the force here, you have this approximation that was worked out by looking at elliptic integral solutions and also verified finite element analysis for this large deflection, which is really nonlinear, but now we have a one parameter model here. As we also saw with elliptic integral, there was just this modulus p that was controlling the behavior of the entire elastic segment, modeled with, in this case, that one parameter is the rotation angle of this, which we can call psi, which will be the angle at the tip of the elastic beam if you take the elastic beam as it is for your analysis. And this was a detailed model. When you have an arbitrary tip load, only force but no moment, then you have the gamma, which we just saw in the previous slide, but also this k theta, which will determine our kappa, that is our torsion spring constant, takes into account the material property, cross section property, as well as the length of the beam. And the gamma again comes here, you have to take this gamma, multiply by k theta and E I by L to get this kappa. So, this is for a beam that has an arbitrary load, that is transverse axial load combination any which way within this range. That is what happens when this beam is as part of a mechanism, a compliant mechanism that has both rigid bodies and elastic segments. There you can use this comfortably and quite accurately, as we will see when we work out examples. Now, let us take beams of different boundary conditions. What if we have a fixed guided beam? What do I mean by guided? It is guided in such a way that it cannot rotate. Fixed is like a cantilever or encaster condition, where the beam cannot move, let us say 2D, cannot move in either translational direction, and at the same time it can also not rotate. Whereas guided one, you allow the translational motions, but do not allow it to rotate. It looks like this. So, we have a beam, this is the fixed connection, this is the fixed connection, the other end here is the guided connection, that is what we call it, guided. As you can see in this model, this point can move in this direction because we have shown that roller over here, and because of this roller over here, it can also move in this direction, but it cannot rotate because it has to be in contact with this, the way it is shown here. But in reality, there are a lot of conditions where you can realize this guided condition. So, when you have fixed guided beam, how do you come up with an equivalent pseudo rigid body model? That is what we will discuss now, because we discussed at length about cantilever beam. Now, we move on to other boundary conditions. If you have fixed guided beam, then it is going to deflect like this. The beam over there, when you apply this force, it is going to deform like this. Okay, that the same beam will deform. In that process, looks like here it is stretched because that length and this length is more. That is because in this slide I have not shown the movement of this in the axial direction. So, we will see that properly, right. So, if you have two beams like this, let us say there are two identical cantilever beams, just for the sake of illustration I put one below the other, but imagine that they are right next to each other. So, both of these, if you fix here at this end and this end, apply force, it is going to deform like this. Okay. Now, again we have broken them down just for the sake of modeling it or imagining how it works, otherwise actually together, right. If you have that, you can think of this as two identical cantilevers where there is a load acting any which way, that is it can be axial, transverse, any combination, that is the n value that we had in the previous slides can be any value, that is -1 to +1 or even -2 +2, whatever value, depends on the ratio of the axial force to the transverse force. When you have this, we can model each one of these cantilever beams as a pseudo rigid body model as we have, because we have broken down a fixed guided beam into two cantilevers, fixed and other one is free, meaning that load can be any which direction, because when a beam bends like this over here, that is like a cantilever because it has a finite slope. So, if you apply a force in some direction, there will be a transverse component and axial component, right. So, when you have that, it is going to deform like this, and that is what we are using to model using PRBs. To have two half PRBs that we put together. The PRB means that we take this length to be a characteristic value gamma times the length of that, in this case L by 2. So, it will be gamma by 2 L for this, and there will be kappa for this. That also we have to see, because earlier if you take cantilever beam there was only one torsion spring, but now we have one here, based on the force we have to take that also as twice of that value, it turns out over here. So, we can replace the cantilever deformation with a pseudo body model. Since there are two of them here, we make a model like this. So, we have the beam which is fixed and guided, and we replace, in fact what I have not shown here is the breaking of this. Okay, that is where the slopes of these two are going to be equal, because as we saw this beam when it deforms, let me draw that beam fixed, let us say fixed here and guided over here. When this moves let us say somewhere here, again remember that it is going to have motion in this direction as well as this direction, then it is going to move like this. Okay. So, when that happens, we said that we break it into two parts, and there is this cantilever, there is that cantilever, because this is other than the little bit of motion in the axial direction, rigid body translation, this is like a cantilever beam, we have broken, that is what is shown here. Two of those we put together, that becomes the pseudo rigid body model for this fixed guided beam. And using this we can think of something like this, where we have replaced a fixed guided beam with a rigid body. So, this one in the middle is a rigid body, and there are two torsional springs. Okay. As we saw earlier, let us go back here to see that now this distance from here to here is 1 minus gamma by 2 L, and same thing over here from here to here, if that is where beam is fixed, and then in between, that is from, let me change the color so we can see clearly, let us say from here to here, that will be again, we have this is gamma by 2 are subtracted, this will become gamma L like what we had, and the kappa here turns out to be 2.25 is what we had. Now, it becomes 4.5 for either of those, because they share the load in a way, because when you break it here there is a force coming on both of them. So, it becomes twice of what we had earlier, because this is like a two springs in series where the spring constant becomes half, that become 2.25 eventually, but both places there is we have a torsion spring, that is over here as well as here. Okay. Let us see how this works in a compliant mechanism context, where you do not have to have this type of sliders. So, if we have something like this, when we apply force over here, that is where we will apply some force. When we do that, it is going to deflect like this. You notice that we are showing both the motion in this direction as well as this direction when you apply force, and that has to happen, right. So, it is going to be from there it comes down here, okay, when it moved. We can also imagine if we have the original elastic beam, it is actually called a parallel motion compliant mechanism or parallel guided compliant mechanism, where the red ones are two elastic beams and this one is a rigid one connecting both of them. This is a rigid body. If you have that, when you apply force over here or the corresponding pseudo rigid body model where you apply a force there, it is going to deform like this, okay, where the beams are bending, and you can see that this red rigid body moves in that direction as well as in that direction. Okay. That is how it is going to deform, and that is how our parallelogram linkage also is going to move, right. So, our parallelogram here moves in this diagram. It looks like the rigid body is stretched a little bit, but that is just a mistake in drawing, but it is a parallelogram linkage that rotates and moves closer to the fixed end, and that we can model with again one parameter, because if you see this parallelogram mechanism, there is only the rotation of this, that is same as rotation here, right, that if we call this theta theta, and that is one parameter for this mechanism, which consists of two elastic beams undergoing large displacement. So, PRB model enables us to analyze things that are complicated. This is not that complicated, the first example. It can be complicated, and we can analyze with a one parameter model by making a 1 degree of freedom pseudo rigid body model of the mechanism. So, here the red one is the real mechanism, the one that we have with rigid bodies, that is this one and this one, and this one anyway was there, is a replacement of this red thing, and 4 joints, and there are torsion springs at all 4 of them, and if you put the values that we have indicated, then your behavior of the pseudo body model will be very close to that of the elastic body one if you were to do finite element analysis and compare. That is what we want to do and see for ourselves that this is a good model to approximate the large displacement, that is nonlinear behavior of a compliant mechanism comprising slender beams. Okay. Now, let us also move to a case where there is a cantilever beam with a moment load, only a moment load. Okay. When we have that, which we had discussed earlier, that in this particular case, if there is a pure moment, the beam which is fixed over here, when there is a moment m acting, this is the undeformed beam, and this will move to this one which is deformed. Since moment is bending moment inside the beam is proportional to curvature, if there is only moment load throughout the beam, the bending moment will be constant, because if you draw the free body diagram, wherever you cut there are no forces, pure moment throughout the beam. So, moment is constant, and hence curvature is also constant, or radius of curvature, that is our rho, is constant for the entire deformed profile of the beam, and the curve that has constant curvature is a circular arc. So, here the beam of length L is deforming into an arc whose length is equal to L, because in this whole theory so far that we have discussed, we do not consider the stretching of the beam. So, here L becomes rho times psi, where psi is the angle subtended by this arc at the center of curvature, which is constant here because rho is constant, right. L equal to rho times psi, that gives us a way of computing psi when you know rho, or rho when you know psi. Okay. And psi again is the tip deflection, because this angle here is same as this angle there. If you see this vertical line is this horizontal line, this normal here is a tangent here. So, that angle is the same. So, that is also the end slope of the cantilever beam when the moment m applied. We know that rho is equal to E I by m, because m is proportional to curvature, rather m is proportional to 1 over rho. 1 over rho is the curvature when rho is the radius of curvature, and the constant of proportionality is this E I, Young's modulus and second moment of area. So, from here we can get psi because it is L by rho, rho we get from here, that becomes ml by E I, which is what we had for this Maisotis method and everything else you have done with small displacement analysis. That holds here even though it is large displacement, because curvature is constant, we do not have to solve the differential equation, it is readily solved for us. Okay. We can get this h, that is when it deflects the free tip, we want to get the locus again. So, that h is given by rho cosine psi, that is this distance, that is rho, and this is psi, rho cosine, actually this should be psi, so it should be rho sine psi. So, not cosine, so this should be rho sine psi. Okay. And the v here, this will be cosine, okay, because this is sine and this is cosine. the vertical one, rho minus rho cosine psi. So, let us correct it, and the slides that we will put up a supplementary file will have these corrections done. So, sin and cos we have, we get this h and v. If we were to plot here, do we see a circle again? So, here what I have taken is our elliptic integral as well finite element analysis solution to plot for various moments. So, moment here is 0, here is some value and so forth. Again the values taken for this are what we had taken previously. E is for steel, length is 1 meter, cross section is 5 centimeter by 1 millimeter, like a strip of steel, and the load here was moment load varied up to 3 Newton meter, 3 Newton meter this moment. Okay. Now, if you see there is again a circle, right. You see this if we draw this dashed line here, that approximates the tip locus of the tip quite well. Here it is almost wrapping around, right. So, for that kind of a deformation, which is practically good enough for most compliant mechanisms, there is a pure moment load, again there is circle. If you see the characteristic length as what we call gamma, we need to find out what that gamma here is, gamma L. Here L is equal to 1. So, gamma is basically that length of that. This is not our 5/6 because it is more than 0.2. Okay. What is that? Why should we take a smaller radius? That we can again see, now that we know that there is a circle, we can fit a circle and find out what that is. That turns out to be 0.7346 times L, where you have to do the optimization, that is you have to minimize the deviation between what you get from the large display analysis of a beam undergoing a moment load, under the moment load, and then circular arc we have to see what this gamma is, and if you minimize the error between the circular arc and this locus that you get from elliptic integral solution, or here we actually have analytical solution, right. So, we do not have to go for numerical solution, and if you minimize that you will get gamma to be this value, and likewise if you look at the torsion spring constant, that turns out to be 1.5164 EI by L. So, we can replace that with this pseudo rigid body model when there is only a moment load. Now, what about a fixed beam? Fixed beam is a little complicated. Unfortunately, this is also the most common thing in compliant mechanisms, and pseudo rigid body model for that is a little bit tricky, because arriving at what gamma we need to take and what kappa we need to take at either end is dependent on the load. So, when these are rigid body connected to other things, at this end there will be transverse force, axial force and moment, and here also there will be axial force, transverse force and moment. They need not be the same, they can be whatever loads that you have, depends on where these two are connected. So, you can certainly model like this, but getting the parameters that hold good for large displacements or deformations of the fixed beam is a little bit difficult, because we have, let us say what we need. If I take a beam that is fixed and another one, let us say the rigid body that was connected, it is not guided anymore, that we already discussed. If I have a beam that has another fixed connection here, let us say this one I take it like this. So, when it goes like this, certainly the curvature is 0 somewhere, it changes sign, let us say from negative to positive curvature over here, but then that does not happen necessarily the midpoint as it happened in the fixed guided case. So, when we allow rotation and translation for this, whichever way it goes, when you take this, where it happens we do not know. Once we know, at that point we can say this is a cantilever beam, this is a cantilever beam of not equal length, unequal length, but we can still do it. So, the trick would be, when you have a fixed beam, we need to know where this point of inflection. So, this is the point of inflection where the curvature is 0 instantaneously, curvature is 0 over there. If we have such a situation, then we need to know at what distance we have that point of inflection. If we know that, then there will be a cantilever this side and that side, and we can develop a model. But then unfortunately, in a compliant mechanism where there are these fixed beam segments, this length, let us call this gamma star or something. That gamma star changes from position to position. In one mechanism it is constant, we can get it and be done with it, but that is not the case. As the mechanism moves, this gamma star also will be varying, and then we will have an extra parameter. We have gamma star as a parameter, and then we have a cantilever beam, the slope at that point, which will be the same for this part of the cantilever beam and the other part, left side and right side. Then there will be another parameter, and that is what we need to do. So, it will not be as elegant as the PRB that we have discussed so far. So, fixed beam is a little bit of a problem, actually not a little bit, a lot of problem to deal with. Okay. Let us note that, and let us see if there is a compliant mechanism like this. We will consider some examples. Can we do this? Can we analyze this? So, if we say that there is some torque over here, can we analyze it, meaning that can we see how this deforms, how the coupler link deforms and so forth. The answer is yes, because this is fixed here and it is movement free over there, load can come any which direction. We know how to deal with that. We can replace this with a pseudo rigid body model where the length is shorter, and put the beam there, put a torsion spring, and we can analyze it. Okay. How about this? We just discussed this, except that it was horizontal, now we made it vertical. We have parallel guided motion compliant mechanism, force is given, length, Young's modulus, I are given. We can analyze this, which we will consider in the next lecture. And what about this? Now, I had put this in the middle like a coupler link, again I put pinned here, meaning that will be there, the movement will be absent. So, we can deal with this because it is fixed and force in any direction. This also can be analyzed by putting a rigid body over here, because I am moving based on that gamma factor, and put a joint there and do this and extend this body like this. So, this one now gets extended, right. So, then we have a regular 4 bar linkage with a torsion spring, we can analyze it. What about this? This is where we have now fixed and fixed, and this will be a problem for different positions of this crank or this coupler. That gamma star I wrote in the one of the previous slides where the point of inflection occurs, that is not known, that keeps changing. So, predicting that and doing it amounts to a lot of work. So, fixed one is difficult to deal with in the pseudo body modeling concept, but we will get an example to see how close it will be, make an approximation, right. Just forget about the fact that it is fixed, take 0.85 as a characteristic factor or some other value and see how close we can get if we were to analyze it using, let us say, finite element analysis and compare it. So, we will look at these few examples in the next lecture. Just to summarize what we have discussed now, this pseudo rigid body model captures kinematic and elastostatic behavior of a cantilever undergoing very large displacements quite well, and it is a one parameter model. That should not surprise us, because elliptic integral solution enabled us to solve the differential equation governing the large displacement behavior cantilever beam with just one parameter p, which is a modulus, or the end slope theta L, they are all related, or eta FL square by EI, they are all equivalent one parameter model that is changed physically in PRB as that psi, which is the rotation of the rigid crank of reduced length. Okay. The other thing we should realize is that pseudo rigid body model enables us to analyze as well as synthesize compliant mechanisms that comprise of a few beam segments that have this different boundary condition we discussed. We discussed a cantilever beam, fixed guided beam, and a beam with end moment only, and fixed beam is a little bit of a problem, we will deal with that when we discuss the examples. And further reading for this lecture, you can look at the paper by Howell and Meadha, as well as the first textbook on compliant mechanisms by Larry Howell. Thank you.